Okay, we are going live now, and let's start. I'll do a short, people will still join us. I'll do a short introduction, and then I will handle to the floor, okay? So let's just record it. Okay, so hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Today, we have the pleasure of having Dr. William Brandt, Professor of Astronomy and Astrophysics and Physics at the Pennsylvania State University. In his vast experience in astronomy, he has first authored and co-authored more than 590 publications in refereed journals with a huge impact in the community. His research focuses on active galaxies, cosmic surveys, starburst and normal galaxies, X-ray binaries, and the galactic center. He is also co-chair of the science collaboration on active galactic nuclei for the LSSD, and an LSSD Science Advisory Committee member. William, thank you very much for having accepted giving us a webinar talk one more time. I'd like to handle you now the floor. Thanks.
Great, thank you. So today I would like to talk to you about some results from cosmic X-ray surveys. We have been blessed over the past couple of decades to have several superb X-ray observatories for surveys work, including here the Chandra X-ray Observatory, the X-ray Multi-Mirror Mission Newton, and NuSTAR. And additionally, we've had SWIFT, and then even more recently, we've had Spectrum Röntgen Gamma with eROSITA and ART-XC. And today I'm going to talk about the results from these three missions I've depicted on this slide. Although for most of the talk, I'm going to focus on results from the Chandra X-ray Observatory. These three missions work very well together. They've been designed to be highly complementary. They fill in each other's weaknesses and overall give us a superb ability to survey supermassive black hole growth over the history of the universe. And today, I will talk about surveys, including the Chandra deep fields, over here as these left two panels. These are the two deepest X-ray observations of the universe that have ever been made, conducted with the Chandra X-ray Observatory, and I'll tell you in all details about them. And then I will also talk about a more recent survey called XMM SURVS, shown here, which covers much wider areas of sky in the LSST deep drilling fields, which I'll again make connections to later on. And so today I am going to focus, as you can tell from the title again, on supermassive black hole growth as revealed by the study of active galactic nuclei. And so this is going to be a talk that has a lot to do about active galactic nuclei, which is one of my main topics of research. I want to thank many people who I've worked with over the past couple of decades on this topic, including many superb graduate students, as well as postdoctoral researchers who have put in heroic efforts on these X-ray survey studies. And I also want to thank many great collaborators worldwide. These are two of our catalog papers recently published, and these are the countries where our primary collaborations have been. This is indeed a worldwide enterprise. And in particular, in my case, I would like to thank the members of the Chandra Advanced CCD Imaging Spectrometer team at Penn State, at MIT, and beyond. And in particular, this was a wonderful instrument on the Chandra X-ray Observatory, led by Professor Gordon Garmeyer, who was a professor at Penn State for many years. He's now a professor emeritus. And ACIS, this instrument, which was used to observe the Chandra deep fields, is a CCD-based X-ray detection system, as you can tell from the name. It sits at the back of this tube on Chandra and actually detects the X-rays from more than about 90% of Chandra's observations. And a wonderful thing about studying or detecting X-rays with the CCD is you don't only perform imaging observations. But while you're performing imaging, you simultaneously perform spectroscopy. That's possible because X-rays are very energetic, and they interact sufficiently strongly with the CCD that they make enough electron hole pairs in the CCD that you can measure the energies of every individual X-ray that strikes the CCDs. And moreover, the CCDs are read out quite rapidly, about every 3 seconds. And so that gives you timing information as well, where you can tell when the X-rays have come in. You can study the variability of the X-ray sources that we're detecting as well. So this is a true imaging, spectrometer, timing instrument all in one. So it gathers an extremely rich data set. So what I'd like to do today then is I'd like to start off by talking about the general utility of X-ray surveys of active galactic nuclei. And I will use this AGN acronym fairly frequently to stand for active galactic nuclei. And I'll talk about why we perform X-ray surveys of active galaxies, why that's a valuable endeavor. I will then talk about the Chandra deep fields, 2 of my favorite X-ray surveys. I'll talk about some selected science results coming from the Chandra deep fields. And then I will end by talking about some exciting future prospects. So let's get on to the utility of X-ray surveys of active galaxies. So there are 3 big reasons why X-ray surveys are extremely effective at finding and studying active galaxies throughout the universe, out into the very distant universe. The first one is that X-ray emission appears to be nearly universal from luminous active galactic nuclei. It comes from the immediate vicinity of the black hole, within tens of black hole radii of the black hole itself. And the X-ray emission is made via Compton upscattering. You have ultraviolet and optical radiation from the accretion disk, and that is Compton upscattered by hot billion Kelvin electrons up in a coronal structure up above the accretion disk, a structure that is perhaps kind of like the solar corona, but far more extreme. And that takes ultraviolet photons, and when they're hit by an electron or perhaps even a positron, and boost them up to become X-rays. So that's where the X-ray emission comes from. And this leads to a nice broadband spectrum of X-ray emission that we observe from these active galaxies. The details of exactly how this spectrum is formed and all of its subtleties are fascinating, but are not essential to this talk. So I won't go through all the details. But what I want to highlight is that we observe this X-ray emission over a very broad band, running from about 0.1 up to more than about 100 keV. So this is a very broad stretch of the electromagnetic spectrum. Remember, the whole optical band is like a factor of 2, okay, in wavelength or in energy. Here we're talking about, orders of magnitude grasp on the electromagnetic spectrum. And to give you a sense of what these observatories are covering, well, Chandra and XMM Newton, in their deep surveys, detect sources most effectively between about 0.3 and 8 keV, so between about here and here. And NuSTAR extends that up to about 16 keV, up to about here. So again, these observatories together cover a very broad bandpass, about 20 times broader than the whole optical bandpass. So you have, again, a very broad stretch of the electromagnetic spectrum that you're covering. And to give you some context, medical X-rays are typically up at 50, 100, 150 keV. So these are lower energy than medical X-rays, but they still are very penetrating, as I'll talk about now. And so that, in fact, is the second reason why these X-ray surveys are really great. And that is that X-ray emission is highly penetrating. We know that from the doctor's office or the dentist's office, and thus have reduced absorption bias. And this is critically important because we know that the light from active galaxies is often, in fact, usually obscured by both material down in the nuclear region, as well as by material on the scale of the host galaxy in which the active nucleus lives. And X-ray emission, being highly penetrating, can get through and can also allow measurement of large absorption column densities. And in fact, that's what this little movie I have here is showing. Here I'm showing the same spectrum that I just talked about on the previous slide, but now I'm adding absorption to it. And this number here is ticking along is the absorption column density. And to give you a sense of what this means in a practical sense, the column density through your hand is about 10 to the 23. So it's like that. And the column density through your chest is about 10 to the 24. So it's about like that. Okay, so it's there. And as you can see, as you increase the absorption present in one of these active galaxies, you get this photoelectric absorption cutoff that marches upward in energy, and it's a strong effect. You can see it spans orders of magnitude in flux. And so by measuring this absorption cutoff, you can quite well estimate how much absorption is present in a given system. The other critical point I want to mention is that, well, the absorption bias drops as you go out to high redshift. As you go out to high redshift, of course, this whole spectrum is cosmologically redshifted downward in energy. And so you gain access to increasingly penetrating rest-frame X-rays. And in fact, when we're studying sources, as we often do out at redshifts of 2, 3, and 4, we have access to these very penetrating X-rays that are hard to absorb. And this lets us get a complete sense of all the obscured active galactic nuclei that are out there in the universe. And we find that there are many, many of them. And then third, the third big reason why X-ray surveys are great is that X-rays have low dilution by host galaxy starlight. And you can see that here. This is just an optical image over here on the left and an X-ray image of a local active galactic nucleus. It's NGC 3783 if you're interested. And the point is that, well, when you look at the same galaxy on the same scale in the X-ray, all the starlight just drops out. And all you see is the black hole related light. And so the point here is that X-rays let you home in on where the black hole accretion is occurring, and you don't get lots of additional light from other sources, such as stars. And this is critically important out at high redshift, because out at high redshift, you don't have the luxury, as you can locally, of going in and spatially resolving away all the AGN light, spatially resolving the AGN light from the starlight. At high redshift, that just isn't possible because the galaxies are too small on the sky. So you need to maximize contrast between black hole light and starlight, and X-rays give you that. Now, best of all, of course, is to combine the X-ray data with multi-wavelength surveys. In fact, that's exactly what we do, and I'll talk about that more in a little bit. Okay, so those are the three reasons why X-ray surveys are very powerful. They give you, for X-ray emission is nearly universal from active galaxies, it's highly penetrating, and it has low dilution by host galaxy starlight. Okay, and so as a result of that, many X-ray surveys have been conducted by those missions I've highlighted over the past several years. And this plot here summarizes all the X-ray surveys that have been done up until quite recently. In fact, this is from a recent review article, which is available on arXiv that I recently published, that gives you an overall summary of the X-ray surveys that have been done. And basically, this is a plot of flux limit along this axis versus solid angle along this axis. And you can see X-ray surveys range from very narrow pencil beam surveys out to quite wide field and even all sky surveys. And generally the wide field surveys are less sensitive and the pencil beam surveys can be very sensitive. And then all the dots are color coded by the missions that have conducted them. So you can see that Chandra, for example, excels at the very deep surveys, whereas XMM Newton is superb at these wider field surveys. And eROSITA has been very powerful recently at the very wide field X-ray surveys. And I'll say more about that later on. But this gives you kind of an overall summary of the X-ray surveys. Now, what I'd like to do now is to home in on my favorite personal surveys, the ones I've worked on for the past couple decades, and these are the Chandra deep fields. Okay, so the Chandra deep fields are the kind of extreme of ultra deep, narrow field pencil beam surveys. They're over here. There's a 7 megasecond observation and a 2 megasecond observation, and here they are. This is the Chandra Deep Field North. This is a 2 million second observation with the Chandra X-ray Observatory gathered over about 2.5 years. And this is the Chandra Deep Field South. It's about a 7 million second observation gathered over about 16 years. And this one is kind of near the Big Dipper up on the sky. And this one, of course, is in the southern constellation of Fornax. And each one of these covers a pretty decent chunk of sky. Here are the numbers. To put that in context, each one covers about 60% the size of the full moon on the sky. And we detect about 755 point sources in the northern field and a little more than 1,000 in the southern field. And the majority of these are active galactic nuclei, 87% and 71%. And again, I want to highlight that we, of course, these are not just X-ray images. We have spectral information and variability information for all the X-ray sources. So I can take a given source, for example, in the Chandra Deep Field South. I can cut out its photons. I can get a spectrum for that source. And I can also look to see how that X-ray source has varied over a 16-year period during the epochs when we were gathering the data. Now, you might also wonder, why is it that there don't seem to be very many sources down here in the central part of the field? And that's mostly an optical illusion. And that's because Chandra's imaging gets considerably worse as you go far off axis, as you can see. But there are many sources down in here. In fact, now I'm going to zoom in just on this box here. And here is that box. This is the same sky region you're seeing right there. And you can see all the X-ray sources that here we've color-coded by their X-ray energies. And these sources are remarkably faint. This is the very deepest patch of X-ray data that we've ever gotten. And to give you a sense of how sensitive Chandra is and how well Chandra was built, the sources that we detect down here, the faintest sources we detect in the center of the Chandra Deep Field South, are such that we get about 1 photon on average every 10 days. And so, that's the length of the exposure, 7 million seconds. And you can still detect sources because Chandra's background is so low, down to about 1 count coming in every 10 days. And those sources are still quite straightforwardly detectable, which is a remarkable thing. Okay, now we of course have we have carefully selected where we have placed the Chandra Deep Fields. This, of course, is the famous Hubble Ultra Deep Field. The Hubble Ultra Deep Field lies right down here in the middle of the Chandra Deep Field South. And there are substantial additional Hubble programs that have been performed in this sky region, including the GOOD survey, shown here, the CANDLES and 3D HST survey, shown in blue. And in fact, in total, according to a recent estimate I saw, there's been about 6 megaseconds of Hubble time, or about 70% of a Hubble cycle, corresponding to about a $250 million investment of Hubble time down in the center of the Chandra Deep Field South as well. And so that's extremely valuable resource for understanding the X-ray sources. And I'll show you some of the nice Hubble imaging of the X-ray sources in just a minute. Of course, we're very excited about the fact that we expect there to be extensive James Webb Space Telescope coverage of the same sky region soon. And we want to combine the X-ray data with the James Webb data as well. And furthermore, there have been many other observational programs on these sky regions. There's been extensive spectroscopy by some of the world's largest telescopes. There has been superb ground-based and space-based infrared imaging, including with Spitzel and Herschel. Some of the deepest programs with these observatories are on these fields. There is superb observations with APEX and now ALMA, growing observations with ALMA in the southern field, and there's superb VLA coverage. And all of these multi-wavelength data are critically important for identifying the sources, just taking the X-ray source and matching it to a counterpart, and then figuring out what is the nature of the X-ray source. Is it an active galaxy? Is it a starburst galaxy? Is it something else? The multi-wavelength data are extremely powerful for letting you figure that out. And they also let you measure host galaxy properties, which I'll talk about in some detail in a little bit, because that's an extremely important part of our studies. And the multi-wavelength data continue to improve rapidly, which is what's kept the science so exciting over the years with the Chandra Deep Fields. Here, I just give a summary of how we're doing with all the multi-wavelength data on getting counterparts and redshifts for the 7 megasecond Chandra Deep Field South X-ray sources. We currently have about 98% of the sources, both having counterparts as well as having redshifts. And so much spectroscopic time has now been spent on these fields that, in fact, the majority, 64.8% of our X-ray sources have spectroscopic redshifts, and about 33% still have photometric redshifts. But the photometric redshifts are very good, typically being derived from like 30 bands of photometric data. And our typical uncertainties you can see here are something around 1% or so, although we do have an outlier fraction of about 6% we'd estimate, but the photometric redshifts seem to be very good. And then that leads to redshift distributions like this. For the active galaxies, the focus of this talk, I show those as the red curve. We detect sources that you can see in decent numbers, running all the way from redshifts of about 1/2 up to redshifts of about 3.5 to 4. And so we have X-ray sources spanning a very broad range of cosmic time. And we use these to work out how black hole growth has progressed throughout the universe. I want to point out we also detect a significant number of galaxies. These are mostly actively star-forming galaxies. They're typically at lower redshifts, out to redshifts of about 1.5 or so. This plot here shows the same data, but binned much more finely. And you can see we detect redshift spikes corresponding to cosmic structures being traced by the active galaxies, which are typically massive galaxies, as we'll see. So they trace cosmic structures very well. So we actually have a good way of finding cosmic structures in these fields with the X-ray follow-up also. So here is an example of the X-ray sources. So in each one of these panels, the circle shows the positional uncertainty measured with Chandra, which has superb X-ray imaging for the X-ray source. And so you can see we can almost always get a reliable counterpart for the X-ray sources. And again, this is Hubble Space Telescope imaging you're seeing in each case. It's a 12 arcsecond by 12 arcsecond image in each case, made from a combination of Hubble Space Telescope B, Z, and infrared imaging. And well, you can see we have lots of active galaxies detected. All these ones labeled as AGNs, these are the active galaxies that we're detecting. And you can see these have a broad range of properties. Some that are quite bright, others that are moderately faint, and others that some like that are extremely faint. Okay, and we have lots and lots of pages like this. In fact, here's another page. Okay, of all it's just showing examples of Hubble Space Telescope imaging of the X-ray sources. Here's another page, and in total, I have like 30 pages like this. And by studying statistically the properties of the galaxies where the black hole growth is occurring, we can learn about the history of black hole growth in the universe. And in fact, that's the main emphasis of what we do. And so that's what I'm going to talk about now. I'll talk about some selected science results from these data. But I can pause here just in case anybody has any questions so far. And if not, I'll launch into the next stuff. Any questions at this point, or is everybody good? Okay, it seems like everyone's good, so I'll continue. So then I would like to now tell you about some selected science results. What do we actually figure out about the universe, from all these wonderful data? Well, one of the big things that we've been working on in recent years is trying to decipher what exactly matters for long-term cosmic black hole growth. You can imagine many properties of a galaxy might promote the growth of its black hole. You might imagine galaxies with large stellar masses might tend to grow their black holes well because they have deep potential wells that can funnel material down onto the black hole. You might imagine that star formation might correlate with black hole growth because star formation requires cold gas, and feeding black holes requires cold gas. And so maybe star formation and black hole growth would be correlated. Or you might imagine something about galaxy structure might matter. For example, the compactness of galaxies, whether a galaxy is highly spread out and diffuse or is tightly clumped together, maybe that would have something to do with black hole growth. Or maybe the cosmic environment, whether a galaxy is in a filament or a void or a cluster or a group, maybe that would have something to do with its black hole growth. And we can address exactly these types of questions. In fact, two excellent students, Guang Yang, shown here, and Qinglin Ni, shown here, have written entire PhD theses largely focused on this question. And we've made a lot of headway. And I'll tell you about some of the things that we've done. Just giving a quick overview. We actually have many papers that I simply can't summarize here, but just give you a quick overview. Well, the first point that I need to make when considering this issue is I want to go back to this. I want to underline that this term long-term cosmic supermassive black hole growth. This long-term aspect is very important, and I want to explain why. So here again is the center of the Chandra Deep Field South, and a natural question that I always wonder when I'm looking at these data is what would this region of sky look like if we hadn't done the Chandra Deep Field South experiment right now, but if we had done it in 1 million years, or in 10 million years, or 100 million years? Would it be the same pattern of spots on the sky, the same pattern of galaxies with black hole growth? Or would in 100 million years, would this image look very different? In other words, should we think of this image as a true representation of what the universe is like always and forever? Or is this just a statistical sampling of the types of galaxies that tend to grow their black holes? And there's much evidence, given that we know active galaxies are highly variable over time, that this is the right viewpoint, that you should think of this as you should think of the Chandra Deep Field South as a statistical sampling of the types of galaxies that tend to grow their black holes. And so what we then do to address these issues of what matters for black hole growth is we take galaxies of a given type galaxies with a given stellar mass or a given star formation rate or a given structural properties and so on. And we average over samples of galaxies of a particular type to try to get at the long-term time average black hole growth in these systems, averaging out the variability that is surely present. In other words, we're taking black hole growth to be ergodic, so that you could average over samples, and that's equivalent to averaging over long time scales. And that's in fact exactly what we do. And we have a good hint that morphology is going to matter a lot for black hole growth from, the well-known results shown here as one example that show how black holes, in terms of their masses, correlate very strongly with the properties of galaxy bulges, both with the total luminosity of the bulge as well as the velocity dispersion of the bulge. And these correlations with bulges are quite strong, and they are not found among other galaxy components. For example, if you look at a black hole's mass and correlate it with a galaxy's total stellar mass, well, there is a correlation there, but it's not nearly as tight as these correlations. So there appears to be something special about the bulge. Similarly, if you look at a galaxy's disk stellar mass, that does not also correlate very strongly with the black hole mass. There's something special about the bulge. And so taking a cue from that, we try to go and investigate the time derivative of this diagram. We want to measure out in the distant universe how this diagram comes about, how it's being manufactured out of the distant universe. Well, the way we can do that is we look at the time derivative of the black hole's mass. That's the black hole's accretion rate or the black hole's growth rate. And we also can look at the time derivative of the black hole's, luminosity of the bulge's luminosity or the bulge's mass, and that would be the bulge's star formation rate. So we try to look at correlations between bulge star formation rate and black hole growth rate. And in fact, we find such correlations, and I want to illustrate those now. So what we do is we use the superb Hubble Space Telescope data that I've told you about, and we investigate a sample of 10,300 galaxies in 5 of the CANDLES fields, including the Chandra deep fields I've told you about, and 3 other well-studied survey fields. And we utilize machine learning-based morphological measurements out of the H-band. So we're measuring rest frame optical light, and we separate galaxies into bulge-dominated systems, shown in these top 2 panels, and non-bulge-dominated systems, shown in these bottom 2 panels, framed in red in the top and blue in the bottom, corresponding to these 2 colors. And why are we doing that? Well, the key idea is to remove non-bulge components for the bulge-dominated sample. And because, as I've said here, we have good reason to think that the black hole's growth rate may well correlate with the growth rate of the bulge, where it probably does not correlate with the disk or with the galaxy as a whole. And so that's the key idea. And well, as written here, we expect that supermassive black hole growth might be related to the star formation rate of the bulge only. And when we then carefully measure the long-term average black hole accretion rate following this reasoning that I've described here, and we utilize bulge-dominated samples so we can get at the star formation rate of just the bulge, we find there is a pretty clear correlation. And here is the correlation. This is our measurement of the long-term average black hole accretion rate versus the bulge-dominated galaxy star formation rate. So that essentially is the star formation rate of the bulge, because the bulge dominates the system. And we find both at redshifts of 0.5 to 1.5 in this top panel, and redshifts of 1.5 to 3 in this bottom panel, a quite clear correlation between the black hole's growth rate and the bulge's growth rate, exactly like you might have expected from this relation. So we can actually see to get black holes and galaxy bulges growing in lockstep over a broad stretch of cosmic history. For comparison, if you look at the non-bulge dominated galaxies, these ones that have strong non-bulge components, well, there might be a bit of a correlation there, but it certainly is much less clear. Okay, and you can see that here again at redshifts of 0.5 to 1.5 and 1.5 to 3. And as you might have expected, things correlate much better with bulges than they do with general galaxy properties. Okay. Now, we can then look quantitatively. We can fit this relation between black hole growth and bulge growth. And here is the fit. Okay, you just fit this thing, black hole accretion rate, long-term average versus star formation rate. And we find that the black hole accretion rate is equal to the star formation rate in log with an offset of 2.48. And then if you work that out quantitatively, that tells you that the black hole accretion rate divided by the star formation rate, time averaged over long stretches of cosmic time, is about 1 part in 302, which is not exactly the same, but is similar to, within striking distance of, the black hole mass bulge mass ratio in the local universe. And so we believe that these results are indeed evidence for coevolution, not coevolution over a broad stretch of cosmic time between black hole growth and galaxy growth, because we observe that directly. Some people have proposed that these results between black hole masses and bulges may simply be an artifact of an averaging effect as galaxies merge together. We don't think that's the case, because we can look instantaneously at instants of cosmic time, and we see that the correlation remains there out to quite high redshift. And again, we hope and are very excited in the near future to extend this work. We would like to go in and measure bulge star formation rates in more galaxies. With JWST, we hope to be able to measure star formation rates in galaxies like these, because these galaxies do have bulges. We just can't get the bulge star formation rate measured very well right now. And we hope to do that in the near future with JWST. And we also, in fact, have work ongoing where we're constraining the gas supplies for black hole growth with ALMA. So that's one example of the types of things that we do. I will also mention just briefly, we've also looked at dependence of black hole growth upon host galaxy compactness. Compactness is a measure of a black hole's mass, of a galaxy's mass compared to its size. It essentially measures how it's a mass to size ratio measurement of a galaxy, where galaxies like this have low compactness, galaxies like this have high compactness. And we find that at least for actively star-forming galaxies, there are also additional interesting, non-trivial correlations between black hole growth and compactness. And again, you can read these papers by Qingling Ni that give all the details. This is a lot of work that I'm just very quickly summarizing here. But we observe compactness correlations as well that can explain additional aspects of the relations between black holes and bulges. Okay, so that's what I wanted to say about that first scientific topic. I have just two more I want to cover. I'd also like to tell you a little bit about supermassive black hole growth in the first galaxies. And Fabio Vito has done a lot of work on this topic, again, using the Chandra deep fields primarily. And Fabio has put in extensive efforts trying to measure the space density and the obscured fraction of high redshift active galaxies down at moderate luminosities. And this plot over here on the left shows one of Fabio's key results. This basically shows the number density of active galaxies versus redshift in different luminosity classes. The luminous ones have already, have long been known for a couple of decades, in fact, have long been known to decline as you go toward high redshift. And that's observed both in the based on optical surveys as well as in the X-rays. And what Fabio has done is he's extended that down to the much more numerous, but individually less luminous, moderate power systems. And as you can see, as you go to lower luminosities, and that's these green points and the red points, they also decline as you go toward high redshift, which is quite interesting. In fact, our measurement suggests that if anything, the decline at low to moderate luminosities is slightly steeper than that at high luminosities, which is somewhat surprising because you might think that there's like a hierarchical growth growing to make the very massive luminous systems, but we don't see evidence for that. As you go to high redshifts, in fact, it appears that the number density of the very luminous systems rises compared to that of the moderate luminosity system, which is a bit surprising, and we're still investigating that. Furthermore, we find that many of the systems out of these high redshifts are quite obscured. This plot here shows our best estimate of the obscured fraction. Okay, these black data points are our best estimates after adjusting for various incompleteness effects. And we find that typically something like 60 to 70 to 80% of the active galaxies out at these high redshifts appear to be quite heavily obscured by column densities of more than 23. So again, this is why X-rays are so critical to address these matters, is if you purely use optically selected samples, we believe you're missing a substantial fraction of the AGM population. Now, we also have worked hard to try to investigate the seeds of the first supermassive black holes. And that this connects to this diagram here, which shows black hole mass versus time after the Big Bang. And of course, we observe now luminous quasars out at redshifts of 6 and 7 and even 7.5. And there's a natural question. Well, how do you manufacture a billion solar mass black hole in just, well, 750 million years after the Big Bang? It's not an easy thing to do. It's not impossible. Some people have suggested you start with stellar remnants around 100 times the mass of our sun, and then these grow via either Eddington limited or hyper Eddington accretion, and can thereby reach the large masses. It's not impossible that could happen, but it's not easy. Other people have suggested that you may have kind of a jump start whereby you have direct collapse of gas clouds forming sort of 10 to the 5 solar mass black holes. And then the requirements for growth are not as extreme to form the first quasars. And so we can address that a little bit with our Chandra deep field data as well. Now, we can't detect these seeds yet. We're just not sensitive enough for that. But what we can do is we can utilize a technique called stacking to set very tight constraints. And so here is the idea of stacking. And this is a nice schematic made by one of my graduate students, Brett Leamer. He put 30 candles on the stairs of his apartment, and he took images of them. He took a 3/100-second exposure. Here's a typical one. And he also took a 1/1000-second exposure. Here's a typical one of those. And the idea of the stacking approach is that, well, if the stacking approach works, then you should be able to stack up these 30 candles, each with a 1/1000-second exposure, and should be able to recover something that looks like that. And here, in fact, is the stack. Okay, and so the point is that with the stacked image, you can recover the candle's wax. The flame is very nicely there. You can even see hints of the wick of the candle. And so we can apply this exact same approach of stacking to either get very sensitive detections or set very sensitive limits on black hole growth out at high redshifts. And that's in fact exactly what we've done. We take the 7 million second Chandra observation, and we then stack up known high redshift galaxies, usually individually undetected high redshift galaxies. And there's lots of them known in these very well-studied survey fields. We have between about 100 and 1400 per bin. And these have let us get average detections or useful upper limits to quite high redshift. In fact, here are a plot showing what we get. So here, for example, is a stack of where we take galaxies of all masses and we stack up. Well, in this case, this has about 1400 of these galaxies, each of which again has about a 7 megasecond exposure. And so you add all those up via the stacking approach. This is like an 8.2 gigasecond or 265 year average observation, on one of these galaxies. And you can see we detect it. There is X-ray flux there. Similarly, here is a 2.7 gigasecond exposure. We detect it. And then at higher redshifts, well, we don't detect it, but we set an extraordinarily tight upper limit with an effective 45-year long Chandra exposure. We also stack the most massive half galaxies. We in fact find that most of the signal comes from the most massive half. And you can see we get nice detections there, comprising most of the signal from all galaxy masses. So most of the X-ray flux comes from the most massive half of the galaxies. We can deduce that. And we then model, try to understand what is the origin of this X-ray emission. And most of the signal that we detect right now is very likely coming from high mass X-ray binary systems. So individual stellar binary systems in these massive galaxies. The population of high mass X-ray binaries in these galaxies collectively makes quite a bit of power. You stack up large numbers of galaxies, we actually get down to a sensitivity where we can detect these things. And so our best estimates now are that most high redshift supermassive black hole accretion occurs in a short AGN phase, the phase where we directly detect the signal, like in this work. And the stacking adds only a small amount of additional power. And you can see that here. This is a plot that shows the black hole accretion density versus redshift for the directly X-ray detected systems as these solid black points, as well as our stacking detections or constraint or upper limits shown as these open symbols. And you can see most of the power comes from the directly detected systems. And this is an extremely important constraint because we've now taken all the galaxies that are out there at those redshifts. We've stacked them all up. We have a total integral constraint on how much power there can be. And it's almost impossible, for example, to hide a lot of additional black hole growth in some sort of a continuous low rate accretion mode. That's very difficult to do based on the quantitative limits that we have. And so our constraints here actually have forced a reconsideration of many previous models, which were up here predicting, well, as you can see, black hole accretion densities far above what our data allow. And so many of these models are rapidly being revised to be in more in agreement with our measurements. Okay. Now, we're very excited about pushing this stacking approach even to higher redshifts. In fact, we have already done stacking of Lyman break galaxy samples out to redshifts of about 8. Currently, we only get upper limits, but we're very excited about James Webb Space Telescope in this respect. I'm sure you all saw this wonderful image from yesterday. My eyes immediately ignored the star, and I started staring at all the galaxies in the background, because my great desire is to go and to take galaxies in our Chandra deep fields out at high redshifts, observed with James Webb Space Telescope, and stack them. And James Webb will provide large samples of high redshift galaxies at higher redshifts with better redshift identifications and better removal of low redshift interlopers. So we'll have cleaner samples as well. And so we aim to push these stacking-based constraints, which can be very tight when you have a large number of galaxies, because the X-ray data are very good. And we aim to push these out to redshifts of 10 to 15 with these samples, using the data from, for example, from James Webb and combining it with the 7 megasecond Chandra Deep Field South. So watch for this in the future. We're getting ready to go do this, and we're quite excited about it. And then I will end just by talking briefly with my final science topic about extragalactic fast X-ray transients. And I'll just have 1 or 2 slides. This will be very quick. But just by accident, we also have stumbled across an interesting class of extragalactic fast X-ray transients, and people like Bin Luo and Franz Bauer and Yongchen Wei and Guang Yang have investigated this quite a bit. So we were analyzing back in 2014 October, we were analyzing new data coming in for the Chandra Deep Field South at the time. And Bin Luo one day came to my office and said, look, there's a new bright X-ray source in our field, and we have millions of seconds of exposure previously that was never detected at all. And this source, we then quickly analyzed the light curve, because again, we have light curve data for all these sources, and we found this source had a quite fast rise, followed by a power law decay, and reached a pretty bright X-ray flux of 5 × 10⁻12. And we got about 115 counts in total in 10 kiloseconds. And we then match it to a host galaxy. It's co-associated with a very faint dwarf galaxy. The redshift is poorly constrained because we can't get a very good photometric redshift at an R-band magnitude of 27.5. But we can deduce that this is a quite low luminosity X-ray transient. And our best modeling suggests that this source may be like an off-axis gamma ray burst afterglow, where a gamma ray burst afterglow was pointed off axis. A gamma ray burst was pointed off axis, so we didn't see the bright flare of the gamma rays, but we do see some of the afterglow emission. So that's what we think is a possibility here. We also then stumbled across another one of these by great good fortune in our data. This one was better constrained. In 2015 March, another one of these events occurred in our Chandra Deep Field. And again, it had a kind of fast rise, followed by, here's a light curve here being filled in, followed by kind of a plateau, and then ultimately a fairly fast decay. And this one is in the outskirts of the 24th magnitude star-forming host galaxy. That's our host. And in this case, the combination of the location being off-centered from the host galaxy, as well as this remarkable light curve plateau, have led us to suggest that this may be a magnetar-powered X-ray transient as the aftermath of a binary neutron star merger. So a pair of neutron stars merged, formed a millisecond magnetar. That led to this plateau phase of quite bright X-ray emission, which ultimately decayed. And the location offset from the galaxy supports that overall idea. And so we're very excited about these fast X-ray transients. In fact, we've now recently, a team of us led by Jonathan Quirola Vasquez and Franz Bauer in Chile have recently conducted a search utilizing the full Chandra archive between 1999 and 2014. And we've now found, 14 more of these X-ray transients. They are the red stars shown here. And this is, in fact, these results from us searching about 170 megaseconds of Chandra data, so an enormous archival search. And further searching for more of these transients from the more recent years of Chandra data is in progress presently. Here are the light curves for the X-ray transients that have been detected. And so we now have quite good rate constraints on how common these transients are. And this provides an exciting science driver for future wide field X-ray missions, which hopefully can detect large numbers of these transients, allow rapid investigation of them so we can study them, in large numbers. So this is another exciting prospect for the future. So I'd like to then end today by talking about some future prospects. I would like to say a few things about X-ray surveys of active galaxies. First of all, we're very fortunate that both Chandra and XMM Newton are still healthy. These missions launched in 1999, and they are still doing great after 23 years now of operations. In fact, this schematic here shows that all of Chandra's subsystems are in pretty good health. And the best estimates are that both Chandra and XMM Newton can likely last until 2027 and beyond. So we hope for like 5 more years plus more years of X-ray surveys. And I think now is the time to take on some really aggressive projects with these missions. And that's in fact what I've been doing. I, for example, proposed a large survey called XMM Serves to get coverage of the LSST deep drilling fields. So as you, I'm sure know, the Rubin Observatory intends to begin its full science operations now in 2024. And it will conduct primarily this legacy survey of space and time over 18,000 square degrees. But in addition, it has picked 4, and there probably will be a 5th field as deep drilling fields. And it will observe these fields much more intensively than the main survey. And each one of these black circles here, these black circles shows a 10 square degree region of the deep drilling fields. These are the 4 fields: Cosmos, XMM LSS, the Chandra Deep Field South that I've been telling you about in this talk is one of the deep drilling fields, as well as LIAS S1. And Rubin is likely going to observe these every 2 to 3 nights in many bands, and will let us do additional exciting active galaxy studies. The concern we had is that there wasn't X-ray coverage over these large areas needed to complement Rubin effectively. And so I proposed to get that. I proposed a 5 million second XMM Newton program, a multi-year heritage program, which has now been successful. And we have now gotten uniform, pretty deep, 50 kilosecond depth XMM Newton X-ray imaging over these fields. In fact, here are the X-ray observations. So this is XMM, this is the XMM LSS field, this is a LIAS S1. Here is the Chandra Deep Field South. Here is the field, the little Chandra Deep Field South field that I've been telling you about for most of this talk today. And now we have beautiful panoramic X-ray imaging all around the Chandra Deep Field South. That's going to be excellent at complementing the wide field coverage that Rubin is giving us. And we intend to use these data. In fact, we're already starting to use these data to investigate supermassive black hole growth across the full range of cosmic environments, because these fields are widely separated on the sky, so they give us a check on cosmic variance. And we're also using the superb multi-wavelength data in these fields to investigate supermassive black hole galaxy connections, like the ones I've been telling you about today. As I've mentioned, these data will have great legacy value as LSST and dark energy survey deep drilling fields. They also are going to get intensive spectroscopy with moons and PFS. The Toltec and ALMA observatories will get superb sub-millimeter observations. We're also doing multi-object spectroscopic reverberation mapping of these same objects. So this is a wonderful legacy data set that I expect we'll all be using for many years to anchor many of the AGN studies with Rubin. And we're also now doing extensive follow-up of these sources. We recently, Fan Zhao, a graduate student of mine, has done spectral energy distribution fitting for all the X-ray sources, but in addition, all the galaxies, which we can now find quite well utilizing the X-ray data to help us in these sky regions. We've uniformly extracted spectral energy distributions running from the infrared all the way out to the X-rays for 2.8 million sources in the deep drilling fields. And we've now systematically fit them using Galaxy, AGN, or bursting and quenching galaxy templates. And we use the Segal code to do this, and we measure stellar mass and star formation rate, again, for the 2.8 million sources. And so we now are starting to characterize the underlying galaxy and AGN populations that are in the deep drilling fields. And we're also excited because there's lots of superb multi-wavelength data coming on XMM serves, ranging from spectroscopic surveys, all these ones shown at the top, as well as radio-based surveys and sub-millimeter surveys. And all these data will be excellent for complementing the Rubin data and the X-ray data. And we're excited about putting all these data together to learn new things about the universe. And I will just end by mentioning that we're also quite excited about new and future X-ray survey missions. We've done a lot with Chandra and XMM, but there's a lot of additional exciting stuff to do. Of course, eRosita launched with great success and has done 4 passes of the sky in its survey. It recently has been shut off due to the troubles with Russia and Ukraine. But eRosita has already gotten superb wide field X-ray coverage, detecting millions of active galaxies that will be fun to investigate on the very wide fields. In addition, we're interested in time domain missions like the Einstein probe, which the Chinese intend to launch in 2023. This will let us investigate many more of these X-ray transients like I talked about. And then we're very excited about missions like Athena, as well as a mid-X mission called StarX, which will let us do superb high throughput surveys, reaching nearly the depths of the Chandra deep fields, but over much larger solid angles, which will let us address many of the problems that I've been discussing today, but with much superior source statistics. So I will wrap up there, and thank you very much for your time.
Thank you very much, William, for this very interesting talk.
Sure.
We now have some time for questions. If you joined us on YouTube, put your question in the comment section and I will redirect it to our speaker. And if you join us on the Zoom, raise your hand and ask your question. So questions? Thaisa, go ahead.
Hello. Hi.
Hi. Thanks very much for your beautiful talk. My question regards something you didn't talk about, was about the environment.
Yes.
Do you have any exciting results regarding environment of AGL?
Yes, I do. If I may just switch, I'm going to just switch to a different slide set quickly. In fact, I have a whole talk on that on YouTube. I didn't have time to talk about that today, but I will try to show you one slide quickly to address that. Okay. I will, but the bottom line is that environment seems to have a rather, and let me be clear. By environment here, I mean large-scale cosmic environment on sort of 1 to 10 megaparsec scales, but sometimes reaching down to sub-megaparsec scales. So let me share the screen again. I have a slide here which I can put up. But yeah, we have investigated that. The prime field to do that with, in fact, is not the Chandra deep fields. The best field to do that with is Cosmos, because you need a large area of sky. So what we've done is we've utilized the Cosmos survey spanning 2 square degrees with superb multi-wavelength data to investigate whether long-term average black hole accretion rate correlates with environment once you control for other factors. You know, we know, as I've talked about, that black hole growth connects a lot to star formation and to stellar mass. And so when you ask the question, does environment matter? You have to be very careful, not because environment is intertwined with mass and star formation. And so we use partial correlation analyses to address that. But briefly, in this paper by Yang et al. 2018, we have looked at exactly your question. Here, for example, we utilize a methodology of Darvish et al. In the Cosmos field to identify galaxies within field environments, filament environments, and cluster environments. Okay, and we look at the long-term average black hole accretion rate versus stellar mass in 3 redshift bins shown here. Okay, and you can see that there, in fact, is rather little statistical difference once you control for stellar mass, okay, between black hole growth in field, filament, and cluster. And if you want to see the full details, again, I have a talk on YouTube, which I'm happy to send the link for, that goes into this in full detail. And anyways, so that's one thing we've done. Furthermore, we also have investigated sub-megaparsec scales using this delta over density parameter, which you're probably familiar with. And again, when we look at that dependence, after controlling for stellar mass, there's rather little dependence upon environment down on sub-megaparsec scales. And here, honestly, we can reach down to like 0.1 to 0.2 megaparsecs. You know, so I'm not going down to stuff going on in the galaxy. I'm
Okay.
going sort of 0.1 to 10 megaparsecs.
Okay.
We don't
Large-
find much quite large scale environments. That's right. And on those scales, we also don't find much evidence for environmental effects either.
Okay.
And again, if you're interested in full details, check this Yang paper. And I have about a 15-minute talk on YouTube targeting exactly this topic. Okay.
Thank you very much.
Yes, thank you. Yes.
Thank you very much, Diazan. More questions?
I'm going to jump back to my main slide because I expect that's
okay.
where the thing will be. So I'm happy to take other questions, but I got to get the other slides loaded up. Okay. Okay, I'm back.
Okay, well, while we wait for more questions, I also have some very
Please.
basic questions
Sure.
from someone from another field. I have actually more than one question. Let me start with the counterparts that you showed on Hubble deep field images in the beginning. For some reason, I was thinking that every galaxy has an active nucleus, but in that images we see that not every galaxy has a counterpart. Is that?
No, absolutely. No. Most galaxies, let me be careful. Most massive galaxies with well-defined nuclear structures to them, bulge components, do contain supermassive black holes. That's what you believe you're referring to. However, most of those black holes at any given time are not active.
Okay.
Though most of those black holes are remnants of black hole growth that occurred long ago in the history of the universe. These were active at one time, but they have now gone off. The black hole has eaten all the available food, so the system is shut off. Okay. And that's kind of what I was referring to back here in terms of when we look at look at our field and ask this question: what would the X-ray image look like if we had done the Chandra Deep Field South experiment, not right now, but in 100 million years? It wouldn't be the same pattern of spots on the sky. I'm almost sure of it because these things vary a lot over time. And so you have to be very careful when trying to make deductions about what matters for black hole growth. You really have to be careful to home in on the actual long-term average black hole growth. If you just use the instantaneous image that you have right now, and you don't treat this as a statistical sampling of the types of galaxies that like to grow their black holes, you can confuse yourself very badly because due to all the shot noise associated with the variability. This will turn your head inside out. You'll just get totally confused. It's very important to use this long-term averaging approach.
Okay, thanks.
Hopefully that's addressing your question. So,
yes.
So only a small fraction of the I showed these images. Let me go back here. I showed this sky image here, of the Hubble ultra deep field. Only a tiny fraction, 1 in 100 or something, of these galaxies are detected as X-ray sources.
Yeah.
Even though many of them contain supermassive black holes, because they grew their black holes at other times, and we missed the growth phase, in the experiment that we did right now. Yeah.
Okay. Let me ask my other question is,
Yes.
you told that you showed us that relation of accretion rate and star formation rates in the bulge.
Yes. Yep.
How do you calculate this star formation rates, like over time?
Okay, right.
It's using
Good.
redshifts.
Yes. Okay. Good. Yeah. How do we get this? Okay. So again, our aim here is to measure the star formation rate of the bulge. So first of all, we home in on galaxies that are bulge-dominated systems. Okay, because again, we do not have the capability right now out of the distant universe to go in and spatially resolve the star formation rate across the scale of the galaxy. I mean, it's very difficult with Hubble even to image the thing at all, let alone to measure the star formation rate spatial dependence across a galaxy. That's a very, very difficult thing to do. It'll be very difficult even with James Webb Space Telescope, but we're going to try. Okay, so instead, what we do is once we have these bulge-dominated systems, we use all the multi-wavelength data And we fit the broad, and by that, what do I mean? Well, I mean all these data that I was referring to back here. In particular, critically important for getting at stellar masses and star formation rates are the infrared data. Okay, so for star formation rate specifically, Herschel is extremely important. For the strongly star forming systems, which are often strongly dust obscured, a lot of their power comes out of the infrared. And so the Herschel data let us from the infrared power, that lets us get at what the star formation rate is. Now, and you probably know this from your studies of stellar systems. And then for lower mass or lower star formation rate systems that are typically less dust obscured, they're typically not detected by Herschel owing to Herschel's more limited sensitivity. So there we use the broadband SED fitting. But essentially what we're doing is we're trying to get at the ultraviolet light, and we're then doing a correction for the dust absorption of the ultraviolet light to try to get at the star formation. So how do we get the star formation? Well, it comes, when we can, we get it from the far infrared. When we can't get it from the far infrared, we go to the ultraviolet and have to dust correct it. So that's how we're getting at it.
Okay, yeah.
And again, I could give a whole 1 hour talk just on that. That is a massive topic in itself. But
well, yeah. now it's pretty clear. Well, thank you. Let me just.
But that's why all these multi-wavelength data are so important. When I was saying host galaxy measurements, you need all these multi-wavelength data to pull apart the host galaxies.
Yeah.
Otherwise, it's hopeless. Yeah.
Let me just ask, are there more questions? Okay, if not, I have a last question. That what is the exposure time? It's like 80 days on
Chandras? That's right. Yeah, that's right. Yeah, we were not messing around when we went for the Chandra Deep Field South. In fact, what we did essentially is we pushed. Let me get the image up here when I went to. So for the Chandra Deep Field South, we essentially pushed Chandra to the limits of the instrumentation. Okay. So Chandra is a remarkable machine. As I said, the faintest sources we're detecting down in here. You're getting one count every 10 days, and we can still detect them down with, as you say, with between these faintest sources have between 5 and 8 counts, and we can still detect them. And that's because Chandra's background is so fantastically low that you can do that. That's due to Chandra's excellent imaging essentially makes that possible. And so, yeah. So go ahead.
This image that you're showing us now, it's a stacking image of many exposures or a single exposure?
Yes, that's right. No, this is this is the 7 megasecond observations constructed from, well, again, from 7 megaseconds of Chandra observations gathered over a 16-year period.
Okay.
Gathered over a 16-year period. And so, and we do interesting things with the time dependence of these things. But again, we push this down. Going beyond 7 megaseconds becomes increasingly inefficient, because we are, by observing that long, we have gotten down to where you're transitioning from being photon limited to being background limited. And when you're and this is not an automatic rapid transition. You start off for short exposures, your sensitivity improves linearly with exposure time, and then it slowly transitions over to being square root. And we're just pushing into square root here. So we've pushed Chandra about as hard as the instrumentation allows. That's why we did 7 megaseconds and not 17 megaseconds or not 2 megaseconds. The 7 megaseconds is naturally set by the limitations of the instrumentation, which is phenomenally good instrumentation. The fact you can go 7 megaseconds is a miracle. That's how well people built this thing. But that's where you kind of run out of steam. And if you want to go deeper, you're going to need new missions that have even better sensitivity than Chandra. And that's hopefully will happen, but it's very challenging.
Yes. Well, thanks. Thaisa has another question, I think.
Yeah, let me take this opportunity and make another question. As you explained about all this stacking and things, how you calculate the average black hole attrition rate from the images?
Okay, right. Yeah, okay, good. Yeah, good. Yeah. So how do we do it? So what we do is, so we take a sample of galaxies with a given set of properties. Let's say we want to look at the dependence of stellar mass. So we take galaxies in bins of stellar mass, and we then measure the average X-ray power from those galaxies. So we take all the individually detected systems, we fit the X-ray data for them, measure the luminosity directly, and then for all the ones that are not X-ray detected, we stack them using the same stacking technique that I mentioned, with the candles. We stack them all up. And then we combine together the direct detections and the stacking to measure the average X-ray power from a set of galaxies with a given set of properties. Okay, and then to get to the black hole accretion rate, well, you have to then convert the X-ray luminosity, which thankfully doesn't have obscuration problems. We don't think very much. If they are, they're mild. You have to then turn the X-ray luminosity into a bolometric luminosity, and we do that either with a straightforward constant bolometric correction factor or with a luminosity dependent bolometric correction factor. The underlying results don't really change depending upon your choice of that. And then then you have a bolometric luminosity. Then you have to go from bolometric luminosity to accretion rate. And that's done assuming a constant black hole accretion efficiency. But again, we've tried different models for black hole accretion efficiencies, and for a reasonable range of models, the results are robust.
Okay.
Does that address it? So, I mean, those are the steps. The steps are analyze the data individually and stack, then get to bolometric, and then get to black hole accretion rate. That's how you get there.
Okay,
and
thank you.
Admittedly, I mean, those are challenging things to do. We've done our honest best to do it. We try different approaches. If someone has a better approach and they want to suggest it to us, we're happy to give it a try. But we found that our basic results, are not subtle little things. I mean, we're talking like order of magnitude effects. I don't go in and try to measure things to 2%. I mean, it's just hopeless. I'm looking at things. I mean, look, this runs from 10 to the minus 4.5 up to 10 to the minus 1.5. And you got 3 orders of magnitude there. I mean, those types of things do matter, and we do them as carefully as we can, but they don't fundamentally change order of magnitude type results. Yep.
Okay. Thank you.
Yep.
Thank you, Thaisa. Well, I think we passed a little bit over our time already, so I'd like to thank everyone, and just say that this presentation will be available on our website and on LIneA's YouTube channel. And thank you everyone for attending, and a special thanks to Dr. Brandt.
Thank you. Thank you for having me. Much appreciated. And again, I hope someday to come visit you all in Brazil when the world opens up again. I'd make it down to Chile, but I've never made it to Brazil. So great.
Okay.
Sure, we will be delighted.
Okay.
Well, take care, everyone.
Okay. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.
Bye. Thank you.